Right, yeah, so I'd like to thank the organizers for giving me the opportunity to speak here and sort of share some line of work that I've been interested in. So yeah, before I begin, I'll just say this is sort of joint work done with grad students Noah, Mariam, and Sam, as well as Michael Gollins at the University of Maryland. Okay. Yeah, so sort of hopefully, you know, by the end of this talk, you'll sort of know what the title means if you weren't familiar with it already. So the first half was talking about what code automorphisms are. The second one is talking about how they work with product codes. And then sort of finally, I'll wrap it all up with an example that sort of showcases all the nice properties. Okay. So sort of the setting I have in mind for this is we know we have these quantum computers with very movable qubits. So either you have your qubits are defined as, you know, some electronic energy levels, either in trapped ions or neutral atoms, and these can be moved either using electromagnetic fields in this so-called QCCD architecture, or you can trap them with optical tweezers, and you can move the laser arrays to move your physical qubits, is what is done in, for example, at QERA. And right, and then sort of from the paradigm of fault tolerance, you know, something that we always want to do when we want to do logical gates on our code is do constant depth circuits. And because constant depth circuits do not spread errors that much. But sort of maybe like a new paradigm when we have these movable qubits and you can do them with very high fidelity and they generically don't really spread errors is that maybe we should sort of relax this requirement to constant depth circuits plus like qubit rearrangement. So this is sort of like the general setting. Okay. So sort of maybe I'll motivate this from like a physics perspective first. Many of you here are probably familiar with just like a Pauli stabilizer Hamiltonian, right? Where it's essentially a commuting projector Hamiltonian. And the ground state subspace, because everything commutes and they're Pauli, is essentially just the simultaneous +1 eigenspace of all both the stabilizer groups. So here I've written SX and SC because I've like restricted to CSS stabilizer Hamiltonians. Right. And then sort of as a reminder, right, like the ground state subspace, the operators that span this are the logical Pauli operators, which you can think about as operators that commute with all your stabilizers, but are not part of the stabilizer groups themselves. Right. And, you know, once we have this Hamiltonian, we can think about like what kind of symmetry operators or what kind of symmetries act on it. And here I'm going to deal with, because, you know, I sort of care about qubit rearrangement, I'm going to talk about this like sort of more generalized symmetry group, which is, you can think about as like the space of internal symmetries, which is first, you know, you can think about, which includes sort of things like your stabilizer groups and your logical operators. Maybe an example is for the toric code, right? These would be like your contractible loops, and these would be like your non-contractible cycles. And then sort of more generally, right, we also have this like spatial symmetry, and these include sort of things like in the toric code would be like a translation symmetry, right? But in general, it's like some permutation of the coordinates. And then the most general form is that you're right, this like permutation, the spatial symmetry can act on your internal symmetries with biconjugation, right? So in general, what this means is that, at least for a CSS code, is your stabilizer and your logical groups are preserved, but sort of the elements inside each group can be mixed, right? And sort of the way to think about it is, right, when you have logical qubits, you have logical operators, and those operators sort of define a basis for the logical group. And when you act on these permutations, they can mix the basis states and they can enact logical transformations. Well, I guess for the toric code, this doesn't really do anything because there's only one logical qubit, but there are other codes which we'll see, which this will do something non-trivial. And then I'll say in terms of the Hamiltonian, right, these spatial symmetries, generically, it only preserves like the spectrum of the code Hamiltonian. So it'll preserve like the ground state subspace where you store all your information, but it won't generically preserve the Hamiltonian itself, but rather just its spectrum. Okay. Yeah. So now, sort of from a more coding theoretic perspective, right? Again, right, the automorphism of a code is essentially a permutation of the coordinates that leaves the code space or the ground state subspace invariant. So like maybe as a simple example of one, here I take the 322 single parity check code. So again, this means there's 3 bits 2 logical bits and the distance is 2 is a classical code. So the parity check matrix is, again, because it's called single parity check, is just 1, 1, 1. And this just enforces that your code words just have even weight. So G is what's called a generator matrix, and the rows of G essentially generate your code space. And you can think about the first row of G as like, logical bit 1, and then this is like logical bit 2. And so here I've written out the code space. I just take, every combination, so 2 squared is 4. And so here are the 4. And you can see if for example, if I swap positions 1 and 2, that's like swapping columns 1 and 2. And that leaves the first 2 code words invariant, but it swaps the last 2 code words. So you can see this permutation does a non-trivial like transformation on the code space. Sort of more like mathematically, right? If I give you a generic generator matrix that lists all your code word generators, right? Saying this, like having a code automorphism is equivalent to saying you act on the right by a permutation matrix. And what happens is essentially that gets pushed through, and there's an equivalent sort of left action by an invertible matrix, right? And the way you can think about it is this condition is just saying that the row space, right, of G times sigma is going to be the same as the row space of G itself, because they're related by a invertible matrix on the left. Yeah, sort of more semantics, just right. These sort of permutations live in what's usually people call the automorphism group of the code. And then these V's on the left live in what we'll call like the logical automorphism group, right? Because V sort of encodes what actually happens to your code words, right? And whereas like sigma is like what you do to the physical coordinates. And then another way to think about it is like G sort of acts like essentially like a group homomorphism between like these two. Right. And then so we talked about G, but then, right, because H is essentially the like orthogonal complement of G, okay, maybe not complement, but orthogonal to G, then there sort of exists like a dual relation, like another invertible matrix W for the parity check matrix H. Sort of any questions on this before I move on? All right, yeah.
And then you have automorphisms of G with a bar on top. What is that?
Oh, yeah. So this is the logical automorphism group. Right? Yeah. So an example is if I give you like the repetition code, right? Right. This one you can permute any of the bits, and that leaves G the same, but it doesn't do anything to the code word, right? So they're like those two are very different. I would say the logical automorphism group is trivial, whereas this one is actually like SN for the repetition code. All right. Yeah, so sort of, why should we care about these things? Well, whenever your code has this permutation symmetry, what can happen is when you have, let's say, a fault-tolerant logical gadget, here I've sort of sketched out a transversal CNOT gate between 2 code blocks, which you would get for any CSS code. Right, because I can just permute the physical qubits and get the same code back, right? You can think about it as I can permute the qubits first and then act on the transversal gate and then sort of unpermute them. But that's equivalent to essentially like hooking up the CNOT gates in, like a different manner between the 2 codes, right? And so code automorphism essentially allows you to do many more transversal gates than you initially thought you had. It essentially like elevates the gadgets you had before to act on more qubits. So there's sort of been work done in the past on the theoretical side for like automorphisms of quantum codes, and sort of recent work on the experimental side. And I would say sort of a lot of the works on theoretical side, the first few dealt with non-LDPC quantum codes, and then the last few ones dealt with like very specific quantum codes. So sort of the question we wanted to ask was sort of, can we study like what is the most generic or very generic ways of making quantum LDPC codes with interesting automorphism groups. Okay. Yeah. So first, let me just discuss some like bounds and limitations, right? You would think like, okay, like there must be some trade-off, like we're getting all this symmetry, like something must be sacrificed. And that's sort of true. I'll just say like, first of all, like, when the logical automorphisms, like these are just linear, like these are just matrices that act linearly on the code space. And so sort of you can think their logical action is just restricted to CNOT gates, at least on the classical level, right? Sort of by similar argument, because permutations can only map polystrings to polystrings, right? You can expect that for a generic stabilizer code, these will only enact Clifford gates. Another question you can ask is, what if I want like the largest possible automorphism group, right? I want this V to be like essentially saturating this bound. I want it to be every invertible K by K matrix, right? Then you can do some simple dimension counting and just see, okay, in that case, like comparing the size of GLK versus the size of the symmetric group, you can see that, okay, there's essentially this upper bound on K if you essentially want to do every single possible automorphism gate. We sort of know an actual family, which this is actually true. You can do the full logical automorphism group, but sort of here the dimension only scales as log n, which sort of suggests like maybe there's sort of more structure than this simple like dimension counting bound gives in this case. The second thing that's sort of useful, which goes back to the earlier question, is like, you know, sort of when is the logical automorphism group actually like equal to the sort of the physical automorphism group? And it turns out there's a very easy condition to check, is just when the dual distance is greater or equal to 3. And just as a reminder, the dual distance is essentially you just switch. So the dual code is you just switch the roles of the parity check matrix and the generator matrix. So here you can think about it as the minimum weight in the row space of the parity check matrix. So to go back to the repetition code analogy, right? The repetition code, it's just 2 body checks, and so there the dual distance would be 2, so it wouldn't satisfy this. But in general, yeah, if you do satisfy this, then these 2 would be equal. You can do a very simple proof, which essentially just show, okay, if 2 permutations give the same logical action, right, then you can show that this operator gets annihilated by the generator matrix, which means this is a code word of, or is in the row space of H, but a sum of 2 permutation matrices has row weight at most 2. So that means the distance must be at most 2. And then also, yeah, I'll also point out there's this nice work has these 2 very similar bounds for these 2 for generic CSS codes. Sort of what I've just said is all at the classical level so far. Okay, so sort of now, hopefully I've given you like a nice quick introduction to like code automorphisms. Now I'll sort of explain like how these fit into the product code constructions. So first, let me just give you a very like a high-level overview of what's called a hypergraph product. Is essentially you have 2 classical codes and you use it to build a quantum code. And intuitively, like because in the quantum CSS code, you need to correct like an X and a Z error, right? So you can think about it as like one classical code is like correcting one of the errors, and the second classical code is like correcting the second error. Like a more geometrical view, I would say, is let me lay out my classical bits and classical checks as like this graph here, and then let me lay out the second code, classical bits and classical checks, and I essentially take a graph product between them, right? And I'll get 4 types of vertices, like bit, check, bit, check, and check vertices. And the hypergraph product is essentially just a dictionary that relabels these 4 vertices into like qubits on the diagonal and X and Z checks. And so here, like, here's what it is like explicitly, and this you can think about this tensor product as doing like rows and column operations. One way to see why like X and Z checks would commute and give you a valid CSS code is because whenever an X and a Z check is connected to a qubit up here, right? Because we're doing a graph product, this edge is always copied down to another edge over here. So there's always another qubit in which this X and Z check will also overlap. So the X and Z checks essentially only overlap 0 times or overlap exactly twice. So everything commutes. The parameters of the hypergraph product code are just related to the parameters of the input classical codes. Here notice that we have a transpose shows up. So actually some of the properties are like the classical codes themselves, but then some of them also come from the properties of the transpose code, which is just the code defined by the transpose parity check matrix. So yeah, another nice thing is if the input codes are LDPC, so if the matrices are sparse, then the output matrices are also sparse. So this is sort of one of the first constructions to make very high rate LDPC codes. Yeah, and then sort of another nice thing is if you look at the logical operators of the hypergraph product code, they essentially mimic the code words of the classical codes along row and columns. So for example, the XL is going to be like a classical code word of C2, and ZL is like a classical code word of C1. Yeah, and sort of a canonical example I would say is if your input codes are 1D repetition codes, then you would get the 2D toric code out of this open and closed boundaries depending on whether you define the repetition code on a line or a ring. Yeah, right. And then you'd have, right, 2 logical qubits for the toric code, right? Like one lives on horizontal links and one lives on vertical links, and that's sort of the 2 different ones here. All right, sort of any questions on this part? Yeah, there's sort of a more algebraic perspective that, you know, you can do all this in, but I'm just giving the geometric interpretation for now. Okay. Yeah. So, right, the intuition is essentially because a hypergraph product code is a product of 2 classical codes. You would say, okay, if the classical codes have some symmetry, then the hypergraph product code should also sort of have, you know, some symmetry as well, right? It turns out this is essentially true. What happens is the thing we act on the qubits, right? Remember that in the classical code, we had both this left. So the right action was the permutation that acted on the physical coordinates, and the left action, this W, was the one that acted on the left side of H, right, in the automorphism condition. For the quantum code, actually, these both become physical things that you act on the qubits. And one way to think about it is because in the hypergraph product code, you have both H as well as its transpose, so you sort of care about both the left and the right sides. And you can quickly just compute, like, if I multiply hx on the right side of this, I can push it through, and this gives me some invertible matrix on the left side. Right, and this tells me that the row space of hx is invariant, so my stabilizer group is preserved. And so it's a valid automorphism. Well, I guess I wouldn't say it's an automorphism strictly because this W might not be a permutation. So that's sort of why we called it like a gadget. But if W is a permutation, then it would be a true automorphism. And I'll get to that later. Yeah, so you can see the structure. Because of the tensor product structure, you're essentially acting like, you know, U1 is like 1, let's say this was U1, and this would act on columns of both the left and the right sector of physical qubits. And then you have an equivalent one, U2, which is essentially identities on the left side of the tensor product, right? And that would act like W2 and sigma 2 on the rows. And so you're right, you have like, you know, this like row and column structure in the hypergraph product code. These 2 things commute, so you can think about like the group that these gadgets will generate, right, as a direct product. And so sort of the total number, like the total size of that group, right, is just essentially just a product of the size of the 2 input automorphism groups. No, it's very loosely, yeah. So it's just like, I think it's like very loose, basically. It's anything you want. Yeah, we didn't want to call it like a strict automorphism because it wasn't a strict permutation, right? Yeah. And also notice, like in the beginning, I talked about like constant depth circuits. Like here, there's no guarantee that W is constant, but sort of, right, the ones you think like maybe we're interested in are the ones where this is a constant depth circuit as well. Yeah. Let's see how much time. Okay. Okay. So yeah, I guess I'll just start this slide maybe from the bottom. We show that, okay, even though you do this permutation, even though you do this circuit W on the right sector of qubits, and that could potentially spread correlated errors, actually the correlations might not be so bad. If you only restrict to the left logical qubits, it turns out there's this nice property of hypergraph product codes that says no matter if you look at all the stabilizer equivalent operators, so if you try to like clean the logical operators, so to speak, with stabilizers, you can never clean its entire weight off of the left qubits. Basically, it's saying like for this logical X, every single logical X still has weight at least D2 on the left sector, right? And what does this tell you? It means, okay, if you do a permutation here, but a circuit here, and the circuit spreads errors, you're still going to need to have at least, you know, D errors on the left side to incur a logical operator. And so that's what we call like distance, like effective distance preservation. And so this is saying like, yeah, you know, the circuit you have to do may not be at least like, you know, so bad if it's like a constant depth circuit. Okay, yeah. So the thing you have to sacrifice here is typically, you know, you sort of just throw away your right logical qubits and you sort of treat them as gauge qubits because that's where the errors can spread. So the nice thing is, you know, typically in hypergraph product codes, most of your qubits are in this left sector anyway. So this is not so bad of a price to pay. Okay. Yeah, let me just briefly also comment on like when these gadgets are actually true automorphisms, right? So here I've like listed the gadgets up here. And right, a true automorphism would be if this W is also a permutation matrix. And so if you actually closely think about what that means I have a permutation on the right side of my parity check matrix that becomes a permutation on the left side of the parity check matrix. And so we call these like Tanner graph automorphisms because the parity check matrix you can describe in terms of this like factor graph called the Tanner graph. And essentially it's saying, okay, permuting the bits is equivalent to permuting the check nodes. And so this is like a sort of graph automorphism. And yeah, maybe from like, to go back to the first slide, right, these like Tanner graph automorphisms you can think about as like actual symmetries of the Hamiltonians themselves, because they essentially just permute the rows of H, but the Hamiltonian was the sum of all the rows anyway, so that remains the same. And yeah, I'll just say like you can also like make all your automorphisms become Tanner graph automorphisms by like a silly way. You essentially just include all of the row space of H into H itself, right? And then everything is just permuting the rows of H, but like then you would lose the LDPC property, so that's not entirely satisfactory. Right, and then lastly, like if your input automorphism gadget was a Tanner graph automorphism, so if these are both permutations, then this U is a permutation, but then notice that this the left action on the hypergraph product parity check matrices is also a permutation. And so actually like a Tanner graph automorphism sort of lifts to a Tanner graph automorphism of the quantum code. And this is sort of going to be a useful property for the next slide. Yeah. So another type of product you can do is called a quantum, is essentially you can take a product of a quantum and a classical code to get another quantum code. An example of this is if you take the 2D toric code and then you take the product of that with a 1D repetition code, you get a 3D toric code. And you can, we can play the same game. There's this nice tensor product structure, and you have left and right qubits. One of the logicals becomes like a membrane, like the 3D toric code. And the sort of the reason you might do this, because you might ask like, well, I already have a quantum code. Why would I like try to build another quantum code? Is that when you do this, right, your Z checks end up becoming highly redundant. And so there's all these, a lot of relations between them, which you can use to deal with measurement errors. And so, yeah, you sort of, you leverage the same tensor product structure and you show like, okay, if I have an input, I've input quantum gadgets and I've input classical gadgets, and the gadgets of the resulting product code follow this similar tensor product structure. And the tensor product structure is nice is because, right, remember that W in general is the circuit we might have to run, right? But because of the tensor product structure, the depth of the gadget is equal to the depth of the input gadget, right? And so if you inputted a constant depth gadget, you would also have a constant depth gadget on the product code. And then lastly, I'll also say, like, if you had a distance preserving gadget like before, you would also get another distance preserving gadget. And I'll sort of just state that without proof for the sake of time. And then also the Tanner graph automorphisms are also inherited. So what's kind of nice is because your Tanner graph automorphisms become the Tanner graph automorphisms of the quantum code, you can sort of like, recursively like build bigger and bigger products of these codes with like bigger and bigger symmetry groups. Hopefully I didn't lose the audience. Okay. Yeah, lastly I'll say you can, last thing is you can take quantum times quantum. And this is like saying, 2D toric and 2D toric gives 4D toric. What was their question? Yeah. Let me go back.
Actually, just for my clarity, the homological product, is this just some tensor product of the chain complex?
It is, yeah.
Okay.
Yeah, I just wanted to sketch it geometrically, but yeah. Basically, a lot of the statements I made before, you can just derive with Kuna theorem. Yeah. So in the quantum times quantum case, like you have, they're both membrane operators, and then you have like meta checks on both sides, like the 4D toric code. But sort of in this case, we were sadly only able to show like this effective fault distance of D1 or D2, right? But not the whole membrane, which is D1 times D2. But that's sort of just I think it's just some like technical, like challenge, but I think morally it's probably true. Okay, so, yeah, I don't know how much information is being conveyed by this table, but we essentially did a survey of a lot of classical codes and how it fits into these automorphism gadgets. I would say the most promising ones are the first 3 rows, because these are the ones that are LDPC, and all the gadgets are actually these Tanner-graph automorphism gadgets, and so everything is truly a permutation. So one is if you're familiar, like cycle codes are just codes defined on graphs, and these two are both popular codes used recently for the construction of like more practical LDPC codes, like bicycle codes. Let me just, with the rest of my time, I'll just sort of give an example that sort of showcases all of these, what can be used, what can these things be useful for. So let me define a cycle code. Let me take the complete graph on 4 vertices, and here are the bits I place on the edges, and the vertices are the parity checks. So it's not too hard to see that essentially a closed cycle is going to be a code word because it will intersect every vertex, twice or none. And so I define 3 logical bits, basically 3 of these triangles. And then notice that because it's a complete graph, I can permute any of the 4 vertices any way I want, and that's going to leave the graph the same. And so that's actually like a graph automorphism. And this actually includes all logical bit permutations. So I can sort of like arbitrarily basically there's no real reason I called these 1, 2, 3 because I can sort of, by the graph symmetry, they're all sort of equivalent. That's another statement of that. So the nice thing is when we have this code defined on a graph, the nice thing when we take the hypergraph products, these codes essentially emit these really nice transversal CZ gates. And sort of one way to think about it is when I take the product of this graph in itself, the resulting quantum code you can think about as a sort of like a toric code, but now defined on this this product graph where I still have the vertex terms and the face terms, but now it's no longer 2D lattice. It's on this product graph. Right. And it's sort of a nice, you get a nice CZ gate, which essentially comes from certain intersection properties of the logical operators. One way to think about it is in the toric code, you have 2 string operators, and then 2 strings sort of always have to intersect no matter how you deform them, right? Roughly 2 or perpendicular strings. If you take further products of this code with itself, right, then you get membrane logicals, and you can say okay, well 3 membranes will always intersect at a point, and that point is an invariant of the homology. And so this actually gives you these really nice transversal gates. And maybe the more algebraic way to say it is that comes from a cut product, which is the way to compute the intersection points. And so this is a certain cut product gate that's defined for this code. Sort of won't go into the details for the sake of time, but on the logical level, I have 6 logical qubits in the left, so 3 in the left sector, 3 in the right sector, and this gate, one of these gates does essentially logical CZ between logical qubits in between 1 and 2, and certain, logical qubit 1L and 1R in between codes 1 and 2, and the reflected version. And with the automorphism gates, what we can do is individually permute all the logical qubits separately, independently between the L and the right sectors, right? So what we can do is say, okay, because we can do this, we can actually have the same gadget address different logical qubits by essentially having the CZs that we apply, just apply to different qubits based on whatever permutation, automorphism we apply onto the input code. And so you can see directly, right, so here the automorphisms allow you to have this original cut product gadget, and the automorphisms allow you to have more addressability with that gadget. And so you can address more logical qubits this way. I will say, if you do a 3-fold product, this would be a CCZ gate between 3 different copies, right? And sort of the same thing would hold. You can have the CCZ address different logical qubits, whatever you want. Well, okay, so I'll also say this particular all logical bit permutations is a very special property of this graph. But you can have, you can sort of think about families of graphs that are highly symmetric that would have very similar properties. Okay, and sort of, I'll just, to sort of conclude, I'll just, say hopefully I've convinced at least the fraction view that looking at permutation symmetries is sort of an interesting thing to look at for codes in terms of fault tolerance. And I'll also say these like automorphisms are very compatible with other gadgets or product codes. The one I sort of just described, you can describe in terms of like higher form symmetries actually, just like intersection point property. And then, yeah, maybe lastly, I'll also say so it's sort of interesting. It would be interesting to see if there's like a family of like high rate LDPC codes where when you do this like permutation plus constant depth circuits, you can like maybe fill in actually the whole logical Clifford group. And that would like dramatically lower the cost of doing fault tolerant computation. Okay, yeah, so thanks for your attention.
Thanks for the talk. Can I ask a quick question? So, did you mention that using a constant depth circuit, you can realize a non-Clifford logical gate in some of these codes?
Yeah, so the one I drew, not in this one, but if you take a threefold product, so maybe you take this hypergraph product code and you tensor it with, another one of these, then you would get something like you would get like a non-local version of a 3D Tor code. And that would have a CCZ gate. And the way to think about it is, right, like in the 3D Tor code, you have membranes, and so you can get 3 membranes to intersect at a point.
Okay.
That's where it comes from.
Do you understand, is there any fundamental limit on what kind of logical gate you can realize by, say, a shallow circuit plus permutation?
Yeah, it's very dependent on like I would say the classical codes you use. So yeah, we weren't able to find any like that filled the whole logical Clifford group, which is sort of why it was like the question at the end. But
okay. Okay, thanks.
Yeah.
Maybe you mentioned this, but do you have any results about whether a given permutation will have a trivial logical action or not?
True. Oh yeah, sorry. It's maybe this thing here. So yeah, the way to think about it, like, right, if a permutation didn't do anything, right, then I would say like the identity plus that permutation, right, would be annihilated by G. And that would say the dual distance would be 2 or lower. So if your dual distance is at least 3, that prevents this, right? That sort of prevents this from happening.
So, okay, can you explain it in the example of the surface code? For example, surface code, there's a trivial reflection. That's a permutation.
Oh.
So I'd say dual distance should be, yeah, okay, could you just walk through that?
Yeah, maybe I'd say for the surface code, like, so for the hypergraph product codes, we sort of like push everything down to the classical level. And I would say for the surface code, because the inputs are repetition codes, right? And the repetition code, the dual distance is 2. Right?
Right,
so that's sort of why. But like, if your classical code had...
this is dual distance. This is result only for hypergraph product, you're saying?
Yeah, sorry. Yeah, this is just for a classical code. Yeah.
I see,
yeah.
Thank you. Sorry for a follow-up question. So, do you, in general, have a way to, like, some maybe new tool to determine whether you, like, what kind of logical actions you get from, like, so is this your main tool?
Yeah, the nice thing we just abused for the hypergraph product codes was the logical basis looks like the classical code words. So it's like we push everything to the classical level, but for if you don't have a nice basis for logical code words, it's hard to say right, because the action is always dependent on how you define your basis.
Do you have any results on like lifted or balanced products?
Yeah, I would say generically for a balanced product code, if the group is abelian, then you would still retain that group as this like graph automorphism. Even I would say, yeah, but if the group is non-abelian, the issue is because you use both the left and right actions, in general, only the center of the group would commute. Okay, another thing you could do is maybe you mod out by a normal subgroup instead of the group itself. Then you sort of retain, like the quotient group would still retain that product structure here. Yeah, I don't know if that answered your question.
No, this is good. Thank you very much.
Okay, I'll ask one question. So can we impose some constraints of locality of the moves that you can do in some real hardware? Like, let's say the atoms, you're allowed to move only in a certain radius and not arbitrarily far.
Yeah, I haven't thought about that, but typically what people have looked at before is translation, just translation symmetry. And so there, like, you just shift the whole lattice by 1 unit or so. But yeah, we were just thinking of more general, like any permutation.
Okay. All right, let's thank the speaker again. And we will get back here at 11.